Thank you, Christian. Thanks to the iBAT Association for giving us the opportunity to present ourselves. We are eightinks. My name is Paul. I'm the CEO. We're freshly incorporated at the end of last year, and we focus on production technologies for solid-state batteries. So our motto, so to speak, is building the next generation of lithium-ion batteries, and they should be sustainable, scalable, and most likely solid. What we are trying to build is a manufacturing platform, so a production platform to unlock mass manufacturing of those novel breakthrough battery materials, solid electrolytes, high capacity anode or cathode materials. And we also think about novel battery designs that are compatible with our manufacturing aspect. And long term, the vision is to build fully circular batteries to store the world's renewable energy. I think this is an approach that every researcher who's working on that topic, who's working on lithium-ion batteries and renewable energies, can get behind. And obviously, it might take a while, but I think batteries are such a versatile tool that we can really strive towards getting the best out of them. Then our team, we are 4 co-founders. You've met me. My name's Paul. The other team members are Leon, my brother, who's been working for Google as in tech delivery and also automotive, and Christina, a former PhD colleague of mine, who's now the CTO. She's a physicist by training and also graduated with a PhD from Vanessa Wood's group at ETH. And Carl Philipp Schlichting is the last of our co-founders, who's also worked in sustainable technologies, membrane technologies, looked into many nanotechnology areas, and he's graduated with his PhD a few months ahead of me. And in the last year, we've also been busy assembling an advisory board that has extensive experience in this sector. First off, Professor Vanessa Wood, who, as I mentioned, is the lead of the Materials and Device Engineering Group at ETH, but also Christian Sorg, who has a lot of tech implementation knowledge at BMW. He has an industrialization and quality background. And next up is Mark, who is the co-founder of Amprius, a Stanford battery startup that went public last year. And lastly, Barbara, who is the CTO at, I would say, Germany's biggest energy scale-up, 1,5. And she helps us support building teams, building technology, and we can learn a lot from these advisors. Then, first up, I thought I'd start by introducing lithium-ion batteries. Obviously, everybody knows about how they function, but I think it's remarkable if you think about that the first commercialization of lithium-ion batteries happened in 1991. With I believe, a Sony camcorder. The performance metrics in terms of specific energy or energy densities, watt-hours per kilogram or watt-hours per liters, were already quite decent. This is what unlocked consumer electronics, portable devices, and from there it went on a success road all the way to automotive. So from 80 watt-hours per kilogram, we've reached over 260, 270 watt-hours per kilogram. And in terms of energy density, we're at hovering around, I believe, just under 700 watt-hours per liters. However, nowadays we're sort of reaching, we think about it as a practical limit. The cell design uses, housings, current collectors, tabbing, all these design aspects that prevent us getting the most out of the theoretical limit of these batteries. So in terms of volumetric energy densities and gravimetric energy densities, the state of the art, which uses liquid electrolytes, is reaching almost a limit. They're still fairly expensive. Well, every once in a while you hear about automakers that promise cheap electric vehicles, under 20,000 francs or dollars, maybe even less, but we're not quite there yet. And in terms of charging times, it's still underwhelming if you need to tell a petrol head that he has to stop for 30 minutes. And two aspects that gain more and more importance are the safety aspect and the sustainability aspect. As the the battery market grows, those 2 points, safety and sustainability, become more and more important. Now, what I briefly mentioned is that if you look at the rocking chair principle of lithium-ion batteries in terms of intercalation, cathode materials, and graphitic anode materials, liquid electrolytes, if you put these materials in a practical cell design, a certain thickness of electrodes with a certain porosity, coupled with housings and sizes, etc., you get to these, estimates, these limits that are represented here by these ellipsoids. And I really liked the publication by Placke, I believe it was in Nature Energy in 2018, that tried to summarize the ceiling of new battery materials and designs. And it becomes quite apparent that the state of the art, it's really difficult to get another factor of 3 out of the performance of these types of batteries. But if you look beyond the state of the art, and their solid state electrolytes are probably closest on the development timeline, you see that this technology shift pushes the limit of battery technology significantly. And this is really, I believe, or what we believe at eightinks, what makes car companies and battery manufacturers pursue these types of designs, these types of materials. Not just, the performance that they show now, but the potential that this technology brings. And in our opinion, the future or the near-term future of lithium-ion batteries is very much linked to the future of e-mobility. The demands that this sector poses to the batteries are very, very high. The performance needs to be very, very good so that the automakers drive the technology development. Not necessarily in-house, but the market has such high demands to this technology that it's really difficult to focus on niche markets. And if you look closer, you can find this basically in every other battery report that focuses on the future of these different markets and sectors. We are past the stage of the early adopters. I think lithium-ion batteries in the electric mobility field are here to stay. It's fairly clear. But the speed at which the market grows is mainly defined by the performance and the cost in the future. So this sector is developing very rapidly. The supply chain is being developed, and this is very hard to predict exactly. But in any case, it's a very, very fast growing sector at a very, very large size, which is unique for our generation. So passenger electric vehicles are the sector that we focus on. And the first realization from our side is that the economies of scale for lithium-ion batteries absolutely matter. And for us, this means it's very difficult to start in a niche market or to start rolling out products for very, very few customers. Instead, you have to really focus on getting a gigascale infrastructure established. And this is where the European market or the European Union in and of itself is a little bit behind. So we really have to think big as a whole ecosystem to get to that place, to get to the ability to manufacture gigascale factories and roll out batteries at the largest possible scale. And you can find academic publications on that, like here from Lukas Mauler in Applied Energy, but also I believe last week or in a couple of last weeks, there was a nice piece in the intercalation substation that talked about the economies of scale of lithium-ion batteries and the margins. And it was clear that, the biggest players in the fields have the highest margins. So, and I think this is something that we have to keep in mind, and that it's not so easy to invest something, for example, on a single player that tries to improve everything. For us, this means that you need to develop a clear focus as a startup, rather than rolling out a gigafactory all by yourself. This is a very, ambitious and goal that might not be so easy to achieve. So we focus on one part of the lithium-ion battery value chain, which is the coating, and I'll get to that later, and try to make that as scalable as possible. With this growth of the sector, it doesn't stop at e-mobility. We've seen, medical devices, consumer electronics, portable devices. We're now in the EVs, but the technology will grow, and I believe, trucking, road transport, or aviation will also build on lithium-ion batteries as the technology improves, as we see the technology shift towards, for example, solid-state batteries. And eventually, these numbers that we produce or that are being produced for lithium-ion batteries will also enable grid storage. Maybe not with the exact same materials, but the cell design, if it's being produced, if it's transferable, I believe grid storage is another promising application for lithium-ion batteries. If you talk to players in the industry, and if you look at academic publications where solid-state batteries are now, I believe the performance of these prototypes are really, really promising. And these types of batteries show a lot of potential. However, it's really difficult to predict when the technology will reach an industrial scale. And I believe one challenge to overcome is the production technology. And this is our lever at eightinks. This is what we focus on. However, I mentioned earlier that the ceiling of solid-state batteries is so much higher than the current state of the art that it fuels investments in this sector significantly. So I believe this technology will come, and it's not a question of when, and not a question of if, but rather when exactly. And if the technology, the production technology is there, I believe we can see the switch rather quickly. I mentioned this in terms of performance values. The prototypes that are being produced by other startups out there depends whether it's going to be, sulfide-based, oxide-based, polymer-based solid electrolytes. They are all somewhere at a different technology readiness level, but none of them are being manufactured at giga scale. Polymers are probably the most advanced, but again, not compared to liquid electrolytes. These numbers don't compare yet. But the prototypes for which the data is available, you can see that they show really good numbers in terms of volumetric energy densities, gravimetric energy densities, charging speed, and safety. Sometimes the size, so the capacity of these prototypes is still not there yet, but in terms of composite batteries or polymer-based batteries, I think we have already seen fairly large devices being rolled out. The remaining challenges that we see at eightinks are mainly centered around cost and sustainability. And cost, obviously, at some point, the performance is not enough if you want to compete with the if you want to compete in the electric vehicle market. So this is really a pillar that's missing. And here on this slide, I would like to introduce also the way that we at eightinks think about batteries in general. So we believe that there are 3 pillars that need to be, mastered to be able to roll out great batteries. And this starts usually with the cell chemistry, the right materials. And you bring those right materials in a functional cell design. And this is typically those 2 areas that the academic world focuses on. And the last pillar that needs to be addressed is the manufacturing aspect. And if you think about it, you can apply this to lead acid batteries, to zinc air batteries. They all look a little bit different. They have similarities, but there are differences that you can trace back to these 3 pillars. So it's really important to think about battery technology holistically. And I mentioned this before, we approach solid state batteries from the manufacturing angle. And at this point, I would like to briefly introduce the typical battery manufacturing steps as they are being followed in today's factories. And this typically starts with a mixing process, right? The active materials are combined with binders, conductive additives, with a suitable solvent to produce a slurry, a material that can be pumped and dosed at the coating station. And at the coating station, you typically have a substrate that functions as the current collector itself. And in many cases, the current collector is deposited from both sides simultaneously, so that you can produce here, we have an aluminum current collector and a cathode material, your cathode electrode. If the solvent is evaporated in the subsequent drying station, you have a roll that can be calendared, that can be compressed to a desired thickness with the desired porosity. It's being shaped to the desired width and the desired length, depending on the cell format. It could be sheets, it could be daughter rolls for 18650 or 21700 cells. And then you get rid of the excess moisture in a vacuum drying step. You continue by assembling your cathode roll with the corresponding anode and the separator. Again, here, depending on the format, there are different ways to do so, either through a Z-folding process where the separator is weaved in between cathode and anode alternating, or you can do a discrete stacking process or winding as you wish for your final cell format. Then obviously you need to combine the current collectors by welding the tabs together, enclose it into a container, and you're almost done. But then you need to infill the electrolyte, the liquid electrolyte, before closing the cell. And this is typically done with a vacuum process. And you cannot ship the cells quite yet. Typically, the electrolyte or the solid electrolyte interface needs to be formed. So you do some formation cycling, some quality testing, depending on the cell format. You degas the byproducts of the formation process, and then and only then you're finished. So it's a very complex process in which many companies and stakeholders are involved. And for solid state electrolytes or batteries, our process started at the point where we thought that we need to be able to develop a solution that is ready to drop in seamlessly. So we didn't want to switch the technology completely, but solid electrolytes should be integrated in this manufacturing process with as little changes as possible. However, they have some requirements that are not quite the same as cathodes or anodes, for example. You want to deposit the electrolytes at a thickness that should be lower than 30 micrometers, ideally as low as possible, as long as they're still functional and provide a uniform coverage. And again, you don't want to introduce a new bottleneck when coating your anode or cathode with these solid electrolyte materials. So the coverage speed should be similar to your anode or cathode speed. So then we end up at the target for solid electrolyte production, for which typically only liquid film coatings are suitable. So we came up with a solution that solves the scalable manufacturing problem of solid state batteries. And this is technology is curtain coating. It's a rather new angle on solid state batteries, but the basic idea is to deposit your active material and your solid electrolyte material at the same time. So rather than pursuing a sequential approach, coating material A and then coating material B, you can combine both or more materials in a single deposition step. It is a liquid deposition technology that's compatible with existing infrastructure. As I said, you can coat multiple layers at the same time. You actually have the ability to coat at much larger speeds, and you have the ability to design your layers, the individual layers, thinner as a state of the art, which makes it especially suitable for solid electrolytes. On the bottom left-hand side, you can see, an image, a rendering of the coating process, where you can see that the curtain is made up of actually two different materials at the same time, and you can, introduce wetting layers or interface layers or other number of layers additionally. So you're not limited in the number of layers. This is what defines our angle on the manufacturing side. And we believe with this technology, we enable actually a wide variety of cell designs, and it remains compatible with most solid electrolytes. Granted, it should be made into a slurry beforehand. So the starting material should be flowable, but for oxides, composite electrolytes, polymers, and sulfides, this is feasible. So it's actually compatible with most solid electrolyte materials. And this defines the technology of eightinks. Now, why is this so relevant? We basically rethink the coating step in the battery manufacturing process that I described beforehand, and we integrate the cell design into the coating step. And this makes the coating step, just marginally more complex, but we do save a lot of capex and opex down the line. So after the coating step, the calendaring process, the shaping process, and the assembly is simplified because the order and the alignment of the functional layers is taken care of within the coating step itself. Obviously, the infilling process is, getting rid of as well. And depending on the type of material that you use for the solid electrolyte, we have a lot of room to save costs in the formatting step. We have modeled this production in the backpack model to include these changes, and we estimate that we can roughly save up to 30% in terms of capex and opex. And this is, again, maybe a good point to restate that we focus on getting the right materials deposited on a material. So the coating step is really the core of our technology, and we actually partner upstream and downstream with companies and institutions to be able to operate lean as a startup. Now, the switch towards solid state batteries, in our opinion, is actually a unique chance to implement a circular economy. For the past 30 years, battery recycling has not been at the top of mind of most companies or people, just because, the scale wasn't quite as relevant. but now recycling is one of the hottest topics ever, rightfully so. But we believe that if we are talking about a new technology like solid-state batteries, we should be talking about this technology in the context of a circular economy. So we believe we should design those batteries with recyclability in mind. So our curtain coating technology, our multi-layer coating technology, actually allows us to do so. And we believe we can shape new industry standards and processes for these types of batteries. And now I think this is a good chance to look into the vision, how we believe these batteries should and could look in the future. And you can see here, grayed out on the left-hand side, a typical, rendering of the inside of a battery. You can see the copper foil, the intercalation anode separated by a polyolefin separator, the cathode material on aluminum. And we actually want to shrink this assembly and make the layers much thinner, but we want to make the whole battery fully coatable. And a fully coatable battery, that we coat with this multi-layer process allows for a simpler recovery of these raw materials, because these cells are dissolvable at the end of life and the materials can be recovered in their particle shape. This is our vision, to keep the battery active materials intact in their particle shape. And lastly, why is this relevant to make the layers thinner? This is actually, probably contrary or opposite to most approaches which follow a thick layer design to maximize gravimetric energy density. But this is basically bound by the use of current collectors that are made up of metal foils. So these have a certain thickness that needs to be kept in order to be able to coat and produce these batteries. If we target a fully coatable design, just by the functionality of transporting electrons, these layers can be made thinner actually. So the electronic conductivity is high enough to make the layers thinner and keep the functionality of the batteries intact. This is a very complex process to be able to integrate in the coating process, but we've made good progress on that front. And this ties together our vision of how batteries should look in the future. And this thin layer design is unique in that sense that it basically pulls the biggest lever for fast charging. The distance that the lithium-ion batteries have to travel within a battery is pretty much linear with the electrode thickness. At least it's the biggest lever. Obviously, we can tune, alignment of electrodes or the conductivity of high-performance materials. But making batteries really thin allows us to charge batteries really fast. It's a fairly simple concept that we have in mind here. All right, and why should battery recycling be reflected in the cell design already? Because we target a direct recycling approach. Direct recycling means basically recovering the active materials, most importantly the cathode active materials, in their particle shape and upcycling them. So we don't have to break down the battery to elementary composites, but if we keep the particles intact and relithiate them to battery grade, we can save a lot of energy. So right now, battery recycling is dependent on many pyrometallurgical processes or hydrometallurgical processes, and this is great and awesome that batteries are being recycled more and more. But again, if we think about next generation battery technology, we should make it as recyclable as we can from the very beginning, which starts with the right cell design. All right. Now, after this excursion into the recycling concept, we would like to introduce how we think about the battery ecosystem. And I mentioned it at the very beginning. The total technology, the overall technology, we believe are strongly pushed by the automotive OEMs and the battery technologies, the gigascale players that are, mainly in China, Asia, and they dictate sort of the pace. But there are many novel or established solid-state startups that propose new materials, new designs already. And lastly, on the right-hand side, these players rely on the right equipment manufacturers, on the, basically the backbone of the technology, these companies that deliver the right machinery and the right equipment to build up these gigascale infrastructures. And we see that there's a gap between these battery manufacturers and the equipment manufacturers. Most battery manufacturers, may it be solid state or CATL or you name it, they would like to have a turnkey solution, a coating line that they can operate without any hurdles. The ease of use is very, very important for these players. And that also goes for solid state startups. Almost none of them have, thought about the right production equipment, and now they have to fit their battery technology with the right equipment that is available. So that's quite a big challenge. And on the other hand side, equipment manufacturers have very limited access to battery know-how. And however, you do need that to be able to operate this equipment very efficiently and with low scrap rates, which, at the gigascale play, you should be able to keep scrap rates to a minimum. So this is where we believe we are sitting at a good place. We combine this production know-how with battery expertise. For solid state, specifically, I think the technology is still at the very beginning. So we might see prototypes soon. For polymers, we might be a little bit further. We might be already at the pilot scale. But the technology generally needs to be targeted bottom up. So to get feedback from the market, from end users, you start with the prototypes, you move to pilot scale, and then you're able to enter mass production. Personally, and at eightinks, we don't believe in the claims that you can roll out solid state within the next 2 years right at the gigascale. There needs to be this bottom-up approach that needs to be verified. The processes need to be dialed in and are so complex that it's very difficult to approach it top-down. I mentioned this earlier, so we are starting out with the coding process. Right now, we have the capability to code 3 layers simultaneously. We can produce layers that are less than 15 microns in thickness, and we can code individual sheets at 120 meters per minute or faster. This is all still in the lab scale. We're preparing the rollout for roll-to-roll manufacturing, but this is what we can do at our own lab at the moment. We can code solid electrolytes. We focus on polymers and composites with ceramics. We can code active materials, both anode and cathode materials. And if in the audience you would like to do trials with an interface layer, customized materials that, for example, help with lithium plating, please reach out to us. I think we can code that as well. We have the production know-how to make it into a great slurry. And in-house, we also have the facilities to characterize the materials and electrodes themselves and assemble coin cells and test these coin cells electrochemically. So for pouch cell devices, we rely on partnerships, but we would like to integrate that by the end of the year in our own facility as well. All right. Now just a couple of images of the technology itself, of the layers and materials that produce. This is a freestanding composite electrolyte film that can be, shaped and formatted for further battery production, and also a cross-sectional view of a typical composite solid electrolyte layer. The white part at the bottom is a metal current collector as a substrate, dummy substrate, and you can see the composition of these individual films. The polymer phase is dark gray, the ceramic phase is light gray, and you can see that we are able to produce really, really dense and uniform thin layer composite electrolyte films. The left-hand side is, I think, just under 14 microns thick. The right-hand side is roughly 28 microns thick. And we have the ability to tune the layer thickness to our desire, or to the desire of our customers. All right. We have been moving into our own facility just a couple of months ago. We're now based in Schlieren, Zurich, and we have built up our own lab facility. We have new team additions. We actually have an open postdoc position at our research partner, the Materials and Device Engineering Group. We are always looking for interns, or if you're looking for a student thesis opportunity, reach out to us. And yeah, growing fast, and it's a challenge for a young startup, but we're quite happy with the progress so far. And lastly, I want to recognize the outstanding support that we've received. We're really happy with our partners and institutions that believe in us, that trust the technology. The project has originally been supported by the ETH Pioneer Fellowship. We have been supported by Switzerland Innovation and the ACS InnoBooster. Currently, we're being supported by the Gilbert Riffe Foundation, Venture Kick, and we have an upcoming InnoSwiss project. And obviously, we still have strong ties to our research group, the Materials and Device Engineering Group at ETH. But we've also partnered with TC Troller, that have the coating secret, as it's written here. They really support us with their production know-how and the manufacturing of these coating dies, and also the Bühler AG that support us with the right infrastructure to scale experiments and the adequate mixing procedures for these types of materials. And lastly, we're part of the Soteria Innovation Group in the US that focuses on battery safety, and we push our coating technology with Gilbert Kugler and his consulting company. And with that, I have reached the end of this presentation, and I'm happy to take any questions or comments. Always eager to learn about battery technology, so feel free to pose any questions.
Yeah, thanks, Paul. So please raise your hands or start the microphone and the camera if you have a direct question to Paul. I think it's a unique chance to get directly in touch with him.
If I may just start, if okay.
Yes.
Christian Jesch from BUS. We are an engineering company near Basel. We're making compounding machines. I'm by far no expert when it comes to batteries in general. I'm coming more from the plastics industry. But everybody's talking about dry electrodes now. Can you tell me how future ready your process is? Because you mentioned a slurry in your multi-layer curtain. Are you looking into that or not?
So the way we see this industry, dry coating is definitely one of the future coating technologies or deposition technologies. We believe dry coating is very, very important for cathodes, but also with the multi-layer coating technology, it could be quite complementary, or I think we even have the edge in many applications because of this thin layer capability. Solid electrolytes or other functional layers within the battery designs need to be very, very thin. And this is very difficult to achieve, with dry coating. So that's one aspect. And the second aspect, and I mentioned this briefly at the very beginning, the ability to make a technology drop-in ready. And there, I think dry coating is still, very difficult to reach production speeds that are required in a gigafactory to make it drop-in ready. So roll-to-roll capabilities, it's feasible with dry coating, I know, but running it at these speeds that you need for the other processes, I think there's still a few open questions. But to summarize, I believe it will be complementary. Cathode dry, probably, anode solid electrolyte. I think this is something where wet deposition technologies will be around for a long while.
Yeah, thank you.
Then we have another question from Janus Ofei. James.
Yeah, thank you for your nice presentation, and it's definitely a fantastic technology, I think. My question is, how do you hinder the different slurries during coating to intermix? And a second question is, how can you control porosity? Maybe each layer needs a different porosity afterwards during calendering, or solid state electrolytes need to be very dense. Can you afterwards heat it up and to densify it afterwards?
Okay, it's a very good question. I think there were actually many questions layered in this one question. So maybe I'll start with saying this. I think the multilayer coating technology actually provides battery manufacturers with the most freedom of design when, targeting different electrode structures. Simply by the fact that you can, start layering different liquid slurries, even within a single electrode, to achieve the desired properties. So for slot die, this is really not possible because, you have one layer and you only have process parameters in drying to sort of tune it. But with multilayer, you can start tuning the composition along your electrode thicknesses or along the thickness of the battery. Why doesn't it mix? This is basically part of our process know-how, but in principle, it's not new because this multi-layer technology has been used in different industries, and it basically relies on a laminar flow on the coating head. And during the deposition, the flow remains laminar and won't allow mixing in between these layers if the properties and wetting properties of the different layers are chosen carefully. And lastly, the comment about different porosities for solid state batteries. This is what it makes what makes the technology so attractive for solid state batteries. You would integrate the electrolyte in your battery during the coating process. So you want a dense layer anyway, and for the dense layer, you can tune the properties of the liquid slurries to the drying procedures. You have this link that you can operate. If you want a porous substrate, you basically have to tune it with the different drying properties. This is similar to the way batteries are produced now. And the final coated electrodes are obviously, being post-processed if needed. So for most cases, I believe calendering will also be part of the solid electrolyte manufacturing. I think this will remain the same. However, I would like to stress that with this technology, we actually have the opportunity to reduce this effort, the calendering effort. Maybe this provides some answers to the question, but I'm happy to discuss further.
Yeah, thank you. So maybe I can add another question. So your technology, what your technology is, of course, the main technology is the coating. So do you want to provide your coating technology to different manufacturing suppliers of coating devices, or can you implement your coating technology to an existing coating machine?
So the coating technology, what we're working towards is having the integration into roll-to-roll facility being seamless. So this is basically the whole, or takes up a lot of our development efforts. And then we have, laid out a few options for us internally how we, market this integration. So both is possible.
Okay, thank you.
Good. Do we have other questions from the audience? That seems not to be the case. So then I would stop the recording.